Hello folks, I wanted to put a video together in response to a post on Facebook from Allison Deneau. She had posted a ledger program that she had wrote for the TRS-80 color computer earlier this week. Allison, I believe, is relatively new to the community. She had a game called Xenocide that was covered maybe a month or so ago on Coco Talk. So it looks like relatively new to the community, but she's definitely contributing some content here and definitely looking forward to future posts by Allison. So this ledger program that she created would allow you to create database records on the TRS-80 color computer and be able to encrypt and decrypt those records if you choose to try to hide those records. So let's go ahead and open up her disk image here. So we'll go into my little utility here, floppy disk tools, and we'll drag and drop the ledger disk here, and we can see that there's a few files that she has on the disk. She's got her ledger program, she's got a demo.dat file. If we click on that, it looks like there's maybe some fake diary entries here. And then she has this Easter egg one that's showing a bunch of characters, and this is an encrypted record here. So what we're going to try to do is crack that record. So let's go ahead and go back to the ledger program, and I'm going to just launch this in VCC. Open this up, and we're presented with the menu program for accessing records, replacing records, creating databases and new records, as well as encrypting and decrypting the database. So just to show you a quick overview of how the tool works, if we select one, we'll look for a particular record, and we'll load her demo file, her demo.dat file, and we'll search for string. So she did have diary entries in there with dates. So let's see if we can find the word May and see if it pops up with anything. And sure enough, it's kicking back records as it finds them for the month of May there. So it looks like it's waiting for a key entry, so we'll hit return and it pops us back. So let's check to see if we can find anything in her egg.dat file, the encrypted one. So we'll do a search, and we'll do egg and see if we can maybe find the same thing. And sure enough, it didn't find anything. There was some disk activity down below. It was searching, and now it's idle. So it doesn't look like it found anything. So we'll go ahead and quit out of this. And basically what she had done is put in her Facebook post kind of a challenge to the community to see if they might be able to crack the encryption that she used on this particular database, the encryption that she has in her program here. So in order to do that, let's go ahead and take a look at the code, and we'll take a look at her ledger program, and I'll view it in here. It's just a little bit easier than looking in the small screen of BASIC. So it detokenized it, and I've got a program listing of it here. So taking a look at her menu, it looks like print 5, encrypt database. If entry is 5, then go to 5,000. So we'll scroll down here, and at 5,000 rem encrypt database. So it looks like what she's doing is she's looking for a database name. So it looks like it's looking for an existing database, and then she asks for a couple key values, key 1 and key 2. So she's using 2 key values to encrypt. Then she opens up the database for record retrieval, and then she does a loop to pull all the strings, all the sectors off the disk that have data in them. And then down here, it looks like what she's doing is she's setting her key value, key $ equals key 1, and then go sub 7,000. So we'll scroll down to 7,000, and it looks like she has an encryption algorithm. So at the top here, basically what she's doing is she's checking the key length against the string length of the record that it retrieved from the disk, and doing some manipulation on it, changing the size of it. And ultimately what it turns out that she's doing is she's setting up the key or the string that she uses to encrypt she's matching that size to the record size. And the reason why she's doing that is down here is where she's actually doing the encryption. She goes for d equals 1 to the length of your entry string, your record, and then she's taking the mid value of that and using d as the iterator. The value of 1, she's taking one character at a time from the input record, and then she's doing the same thing from the key record. And basically what she's doing is she's adding the ASCII value of the string from the record to the ASCII value of the key. And if the value happens to be over 255, we know that we can only go 0 to 255 for our ASCII values. Then she subtracts 255 from it. And then she concatenates the string to build her encrypted string. So it goes through, does that whole iteration, changes the record A to D, so this D that was concatenated goes into A, and then we do a return. So we go back up to 5000 where we were doing the encryption, and we did our initial go sub 7000. She sets the key value now to key 2, and then she goes to 7000 and she goes through the whole iteration all over again with the second key. So, with that being said, we have a decent knowledge of how she's doing the encryption, but without the keys, it may seem somewhat simple, but it's still quite complex. There's a lot of different options here with the keys, and as such, the encryption that she's using will basically prevent us from brute forcing this. Essentially what she's doing here is she's using, it's kind of a ROT, for those that may be familiar with cryptography, it's kind of similar to a ROT 13 or a Caesar cipher, but what she's actually doing, it's a polyalphabetic cipher because she's changing the value of the key for each character that we're encrypting in our string. And what that ultimately amounts to is a space. And for example, a space in the string that you're encrypting is not always going to encrypt to the same value. So looking for those types of values, looking for those types of patterns, you would think that E would be the most popular character that would appear in a string. That's going to be, the encryption for that is going to be different each and every time because you're cycling through the different characters in the key to create that rotation. But it does work to our advantage. So a couple things happen here. So one thing that it works to our advantage, she's using the same algorithm for both encryption passes. And basically what that means is the use of a second key is incidental in this case. And we'll see this in a minute through the tool that I created to decipher her encoded messages. But as long as we keep one of the keys static, we only have to really focus on revealing a second key. The other thing, too, is because of the way that she's got this structured and using the same algorithm, the key order really doesn't matter. We can swap key 1 and key 2, and it'll still yield the same results. So that definitely plays to our advantage. But by shifting the keys, we have almost an infinite number of key pairs that will work to decrypt the message. And I'll show you how that works in just a minute. So I'll go ahead and bring up the tool that I had put together to work on the decryption of this. And it looks like there's a lot going on here. I really only spent maybe about an hour or so putting this together because I started taking a look at it and figuring that brute forcing this, just trying iterations through different ASCII values would just take a long time. The other downside to that is you really need to have eyes on the decryption as it's happening, or on the brute force attempts as they're happening, unless you have some sort of dictionary set up where it's looking for strings, known strings, in the decrypted plain text. So as it's going through and trying to decrypt the ciphertext, you would need eyes on the output to make sure that it's legitimate values. So this tool definitely helped me crack this much quicker than if I was trying to do it by hand. or trying to do a brute force method. There's still a little bit of brute forcing happening in trial and error, but as you'll see, this definitely makes it a bit easier. So basically, the tool split up into two different sections. Up top is where I actually work the problem, and down below, these values are actually pre-populated from her 4 entries that she has in her encrypted file. And I'll just bring that back up for a second here. So we'll go back to our edit view. We'll look at egg. And you can see there's some remnants of clear text here that are from their diary entry. Looks like it was there on the disk at one point. But what we'll do is we'll take a look at our first characters here. Start with F4DDBFC9, and that's exactly what we have down here in our output hex, which is our ciphertext. So all I did basically was take the 4 entries that she has here and copied those directly into the program, and I have those as static values. It makes it much easier to work with, and as I'm trying to crack the ciphertext, I have eyes on all 4 outputs simultaneously, which makes it much easier to do. So up top here, we basically have a couple text boxes where we can input a text value, we can input a hex value, and then down here we've got an output for text and hex. And I can switch between inputting text or inputting hex, and then I also have automatic encryption and decryption happening on the fly, and I can also do a manual if I want to. So what I'm going to do, just to show you how the tool works real quick, is we'll just put in a plain text value of crack this message. So as you see, as I typed it out, it populated hex values out here, and then here's our output text. And the reason why it's the same as our input text is because we have no key values in here. But as soon as I start putting in key values on the fly, you can see things encrypting and decrypting. And the reason why they're changing down below here is because I have all the outputs simultaneously updating as we're changing the key pairs, and that significantly helps as we're trying to figure out the actual clear text, or what the key pairs should be for deciphering to clear text. So if you take a look here, we have our output text, which is our ciphertext. Here's our clear text, and our output hex is our cipher output hex as well. So just to show you a little bit on how this works, a little bit more on how this works. If we were to take, say, ABC as our encryption, and then also use CBA, as our key 2, you can see that we've got a certain value that outputs here. What I'm going to do, though, is I'm going to swap these 2 values, and if you pay close attention here, it produces the same result. So another thing here to be mindful of is the fact that we can show how almost an infinite number of key pairs are possible to encrypt and decrypt the same message. So what I'm going to do is I'm going to change this to ABC, and down here we'll change this to 345. And if you notice the output hex here, what we have is this here. So BC, CA, B9, B7. So this is the same. And what I'm going to do, just to show you how this shift of the rotational value works with her keys, we can use different keys to decrypt or encrypt to the same result. And what I'm going to do is shift this up by 1, so we go BCD, but to compensate for that, what we're going to do is we're going to downshift here. So we go 2, 3, 4. And if I come back to my text, let me grab that just off the edge of the screen. There it is there. Okay, so if we take a look at that, it's yielding the same results. So that greatly works to our advantage, because typically what you want in an encryption scenario is you want to have keys only encrypt to one value, and only those keys will work to decrypt to the reciprocal value. You do not want to have multiple key pairs yield the same results because that makes things much easier to crack, as we'll see in a minute here. So getting back to, so now that you have a kind of a high-level overview of how this tool works, what we're going to do is we're going to attempt to crack Allison's messages here. And to do that, basically what I can do is any of these 4 values down here, I can copy to my working setup here. So we'll start with number 1 down here, and we'll copy that up. And we have no key values in there. What I'm going to do to show you that the key values are kind of incidental, or using a second key as incidental here, is I'm just going to set this to a static value. I can set it to absolutely anything that I want. I'm just going to set it to 0. As you can see, it changed the output here. But now what I want to do, first I want to set it to decrypt. We're no longer encrypting, we're decrypting. And what I want to do is I want to start searching for some phrases here. And the way that the tool works is it starts from the beginning. You can do searches for the middle, and that's what I had actually started to do, but it does not yield any type of useful results because, again, you have to have the beginning of your key set before you can work on the middle. But the way that the rolling encryption works, because she's starting from the beginning and working all the way to the end, we can start from the beginning with trying to decipher her messages. And the way that we do that is I can say, okay, what are some popular words that these phrases could start out with? So any of these output text, what are some of the messages she could have said? So at first I took a look and said, okay, maybe congratulations. So we'll say congratulations. And one thing I should mention here, I'm making an assumption. It's all in capitals. And the reason why is because the color computer natively is all caps. And I'm assuming that, oops, I spelled that wrong. I'm assuming that her clear text and the keys that she used are most likely in capitals as well. She said that it could be any character that the color computer can type, but for the time being, I'm just going to assume it's all capitals. I'm going to assume A through Z, as well as alphanumeric 1 through 0, and any of the shift characters and whatnot. But let's start with this and see where it gets us. So once I type in a search phrase, what I can do is I can do find key, and then it does a search. It's kind of a brute force search, but goes really quick. And all it's doing is it's matching this value here against these first few characters here, however long the word congratulations is, to see if it can produce a match. And as you can see, once I hit copy into this key field, it did find a match. You can see that it says congratulations. Great, we're well on our way to deciphering this message. But wait a second. This particular key, while it is creating a decipherable message for these characters here, this is still garbage. I have a C there and then a paren, but I doubt that's anything. There's semicolon U equals. So I highly doubt that that's the case for this particular message. So what I can do is, all right, let's try it with the second message here. And we'll do find key again. And that yields a different result. So if I copy there, we see congratulations, but again, garbage. Nothing there on the other strings. So I can go successively through all these, hit find key, and oops, did I do copy 3? Copy that over. We've got congratulations there, but garbage on the other ones. And then we'll try with 4, find key. That one went pretty quick. Copy that over. Congratulations there. All garbage. So it looks like the first word of her, any of her records here is definitely not congratulations. So let's try something else. Let's try the. Something a little bit easier. And we'll do find key. Copy over. So we've got the on output 4, but garbage here. TBF, maybe, but that doesn't seem like a word to me. And then we can go through again and we can, just iterate through the process. And it seems like this takes a long time, and it does, but once you get started, it moves really fast. And I'll show you that in just a second. So we copy that over. There's there's nothing there, nothing there. We'll try that one there. Find key, copy it in. That works. Nowhere else. TND, maybe, but I get garbage in the other ones. So let's try this last one. Find key, PEJ, copy that over. The LH, maybe, but I doubt it. T with quotes, LN, so I doubt that's it as well. So we tried congratulations, we tried we tried you. Let's see if. Let's do a find key on that one. Copy over. Whoa, wait a second. So we've got if there, AF there, I space there, AL there, ALG, but we only have 2 characters there, so it's only AL for the time being. Let's do if space. Find key, copy that over, if space, AFT, I space, ALS. Hey, we might be onto something with this one. So, AFT, so that might be after. So we hit a copy of that. We'll copy this working value up to here, paste this here, hit find key. Oh, we need to type after, and then a space after that because the space counts. So we hit find key, and hey, it's reproducing the same key, just extending it. Copy that over, and look at that. We've got after, ISUR, also comma, if you. So we are definitely onto something. So now this is where things start to pick up. So this is where we start trying to figure out more words and work through the process. So let's see, which one do we want to pick next? I sure. What would be a good word after I sure? I sure like, I sure. How about I sure hope? And again, we copy this as our working set up to here. I think that went through. Then we hit find key, and look at that, it's extending even further. Copied this to our next key, and it looks like we're on our way, guys. So if you are after all, comma I sure hope. Also, this is an easy one to grab here. Also remember. So we'll copy this up. Oops, we got to make sure to use caps. Also remember. Copy this over. Also remember, I sure hope we, if you are read, if you are read, all I something. So I'm going to guess if you are reading and I'm going to say maybe the next word after that would be this. So let's hit find key. It's going through and calculating. Copy this over. If you are reading this, after all, I did not make maybe. I sure hope we can have. Also remember to drink. I wonder what that is. If you are reading this, after all, I did not make. I sure hope we can have. Let's see what we got here. Drink your space. Copy this up. Find key. Copy this over. Also remember to drink your, if you're reading this then, after all, I did not make this. I sure hope we can have a TAL talk. I think I know what this one is. And this is great that she did this. this is copied up. And it looks like it extended the key. And it looks like there's a character after that. Also remember to drink your Ovaltine. That's great, Allison. I love that you put that in there. I sure hope we can have a talk about something. After all, I did not make this easy. If you are reading this, then you are. Where do we go from here? Talk about, let's see, talk about how space copy that over. Yep. After all, so it looks like we got the exclamation point at the end of Ovaltine. So there's phrase 1 completely deciphered. If you are reading this and you are in definite, and after all, if I did not make this easy, since we'll copy this up to our working set. Since, let's see, since, and it goes pretty quick, even though, it's kind of a brute force. We're helping it along by, doing some of the deciphering ourselves. So it's, just doing a match at this point. Copy that over. After all, I did not make this easy. Since if you are reading this, then you are indeed, not sure. So we can get a couple more characters there. Copy that up. I'll copy the key over. Since you space, since I space, indeed a copy this up. It goes, taking a little bit longer now as it's brute forcing. Copy that over. Did we get any more since? Oh, I need to add a space there. Gives us one more character. Hit find key. Since I U, let's see if that might be used. And the further we get into this, if these were longer, obviously take much longer. But again, because of us hitting these right away, it's going much quicker than it would if we just purely brute forced it. Copy that over. Since I used, you are indeed a mighty. Okay. We got to copy that up. Oh, and it looks like we got something there. Approached. Maybe approached. Copied that over. Yep, so we can do approached. Copy that in. Here we go. How you approached. Not sure what's next. I used two PA something. PA something, two parts maybe. Let's see here. Mighty code. Indeed, a mighty code. I'm gonna venture a guess, and that's breaker. Copy that up. Find key. So you can see how having all four of these messages simultaneously decoding as we're stepping through this makes it much easier to try to figure it out rather than doing one by one, which I had initially started doing, and I was kind of doing it a little bit by hand, but this, I took maybe, like I said, an hour to put this utility together just so I could see if I could start cranking through it a little bit quicker. And there we go, Mighty Code Breaker. Since I used 2 passes with, and I should approach Decipher I. So deciphering maybe. So we'll put that in there. Copy 3. Deciphering. And I'm going to say deciphering this message. It looks like that might fit. And we do find, did I copy 3? Yep, I did. Find, that went really quick. Copy that in there. And sure enough, there we go, how you approach deciphering this message. After all, I did not make this easy since I used 2 passes with 2 separate, I'm going to say that's keys maybe. My hat is of, so maybe off. So let's see what we get here by putting this up there. We do keys, copy 2, we do our find key value. That went super fast. And it looks like there's an exclamation point or period or maybe something else at the, my hat is off, and I think that's probably to you. And copy 1 up there, find key, copy this over, and sure enough, that's what it is. We've got our period there, so we've got 3 of the messages successfully decoded. So it looks like we might have one more character there, and we'll try period and see if we get deciphered character there. Copy that over, and sure enough, there we go. We've got our 4 deciphered messages. If you are reading this, then you are indeed a mighty code breaker. My hat is off to you. After all, I did not make this easy since I used 2 passes with 2 separate keys. I sure hope we can have a talk about how you approach deciphering this message, and also remember to drink your Ovaltine. Great nod to Ralphie in A Christmas Story there. I love that. I cracked up when I saw that. That was the first message that actually popped up as I decoded it. So I kind of left it at that for a little bit, and then it occurred to me that it might be difficult to find her keys. Obviously, I don't think Allison used these 2 as her key pairs to decipher this. But as I gave it some more thought, it occurred to me that if I could basically come up with guessing to figure out what one of her keys might be, I might be able to have the ability to reverse this and figure out what her actual key pair is. And sure enough, the way that the algorithm works, I can definitely do that. And the way that I go about doing that is I take my known good key here, which is this value here, and I can just start putting in random values for key number 2 and see if the possible key that spits out, given that we have a legitimate passphrase that matches here, it'll reverse to show me some clear text here. So let's go ahead and do that. So knowing that Allison had posted this to the Facebook group, posted in the community, my thought it would have something to do with Allison or the community or something thereof. So I basically just started, random guessing some things, tried Allison, and we do find key. That's producing garbage. I don't see anything there. Let's try Coco. And again, even if I just get the first one right, we should start to see some legitimate text there, or first couple characters right. We hit find key. Don't see anything there. Maybe TRS-80. See what that gets us. Aha! Well, look at that. We're onto something. Welcome. So it's missing the E, but let's see if we can elaborate a little bit more on this. TRS-80 color computer. Find key. And would you look at that? Welcome to Coco Talk. A nod to Stevie and the community. And what's happening here is you're seeing the repeat of that key, because we have this key iterated out so far that it's just going back to, again, her algorithm, how she just basically concatenates the key over and over again to match the phrase length. So all we need to do is just take the Welcome to Coco Talk part. Well, actually, before I do that, I can show you how this works on the fly. So I can just type it in the window. And as you can see, as I type it out, you can see it filling in these values down here. How it's going character by character, word by word, and deciphering our message. And that's how I figured out what her key pair were, the 2 keys that she used. A little bit of luck there, obviously. I took a little bit of guessing, but, having a little bit of knowledge of, Allison's approach to this, definitely helped there. So Allison, again, thank you. This was fantastic. I had a lot of fun doing it, and it was a great great contribution to the community. Definitely hope to see more from you in the future, and my hat's off to you for doing this. So Allison, the rest of the community, take care. This has been a lot of fun.